Assalamualaikum and good day. Today we're going to learn about the new chapter which is chapter 5, frequency response and Bode plot part 1. Okay, the outline of these chapters is that the introduction, transfer function, frequency response plot, Bode plot, and real poles and zeros. Introduction. Okay, the frequency response of a circuit describes the relationship between the amplitude and phase angle of the input and output sinusoid, which are frequency dependent. Okay, from the word here, if we going to make it the important points is that the amplitude and phase angles of the input and output. Okay, and of course it is a frequency dependent because we have it in omega terms, right, which is the frequency 2 pi f. Bode plot is a generalization of obtaining the frequency response of a network based on the transfer function. Okay, the transfer function is our h, right, which is the when you time with your input, you're going to have your output. Okay, that is your h, the transfer function. Okay, so if you can see the frequency response here of a circuit describe the relationship between the amplitude and phase angle of input and outputs. So the one that relating your input and output is your transfer function, the h. Okay, Bode plot allow us to approximate the frequency response of a circuit using straight line approximations. So we're going to have a straight line variations, okay, and become the industry standard method of presenting frequency response informations. Okay, so Bode plot actually often being used in industries. Okay, application, most network behave or act as a filters. Many applications need to retain component in a given range of frequencies. Okay, if you can see in filters, right, as you have learned, it is about filters which allow certain frequency and this and not allowing the other frequency. It is in range. Okay, in certain range. Okay, many applications need to retain component in a given range of frequency and discard the component in another range. This can be accomplished by the use of electrical network, which we call filters. Okay, so you can have 4 types of filters. We can have a band stop filter, pass band filter, a band pass filters, low pass filter, and high pass filter. Whereas the band, we can call it pass band, stop band. Okay, that is actually the band when we call for it. Okay, so it's different. Band stop filter, but what is the band which is stopping the frequency? Stop band. Okay, something like that. Transfer function defined as the ratio of the phasor output voltage. You can see here is a phasor output voltage to the phasor input voltage. So this is the important points, which are the ratio. Okay, output voltage to the input voltage as a function of frequency, of course. Magnitude of transfer function shows how the amplitude of each frequency component is affected by the network. Phase of transfer function shows how the phase of each frequency component is affected by network. Okay, you can see here, we can see the amplitude is there and we can see the phase is there. Okay, so there is 2 important things also that you need to look, which is the amplitude and the phase. Okay, let me see this example one. Find the transfer function of the network below given as Hs equals to V of V2 over V1. So if you see here, this is your V1, which can be like your supplied voltage or input voltage. This one as you can regard it as the output voltage because it is measured across C and it is taken as V2. Okay. So and then the component is where we measure our V2 is our capacitor. Okay. So first, as you learn from your circuit theory, by voltage division, this one is in series. Am I correct? So if we were to get this voltage information, it must be V2, the voltage drop here, voltage measure here, over the total voltage, which is voltage contributed by this component and this component. Okay, because by voltage, by KVL, you know that the V here is the same as here. Okay. Okay, I'm going to change the screen. Okay, I think you already have this slide. Then I would like to do some explanation using the screen. Okay. Okay, the first circuit. Okay, you have your circuit here, which is taken as V1. Am I correct? Sorry, I forget to share the screen. Okay, you have this as your V1. Okay, and then you have your resistor here, and you have your capacitor. Here, measured as V2. Am I correct? Measured as V2. Okay, and then you have a resistor here, and then it is given that the Hs is actually V2 over V1. Okay, so by voltage division, you know actually the the Hs is equals to, which is, let's say you take this one as a resistor, right? Voltage contribute by the resistor. Let's say you can put here is a VR. Okay, for example, okay. Then by voltage division by V2 over V1, okay, this is the input voltage, the total, and this is the uh, voltage measured at V2. So by total here, this one is actually VR. Okay, VR plus V2. Am I correct? And then you have this one as V2. Okay. Then you know all of them is actually relate to the same current. Okay, the same current. IR, IR. So here we only want to see the Z2. Okay, here is ZR, here is Z2. Okay, you know for the impedance of Z2. Okay, I'm a bit explain a bit long here because I want to make sure that you understand. Okay, So Z2 is the capacitor. Okay, the capacitor, you know, actually capacitor is actually 1 over j omega c. Am I correct? 1 over j omega c. Okay, and then the resistance, nothing happened. It's just a resistor here. Okay, and plus with your another your capacitor 1j omega c. Okay, sorry. And then here where we introduce wait for a while. Okay, here we introduce this, which we know that S equals to sigma. I do this is not really I forget this pronunciation, plus j omega. Okay, and at steady state, okay, at steady state, this can be regarded as 0. Okay, at steady state, and therefore your S is equals to j omega. Okay, so this one bring upward here. Okay, Hs. Now we do the replacement. So j omega here, it will be 1 over Sc, and R plus 1 over Sc. Okay, small s, capital C. C is the capacitance value. Okay, and then you need to do some rearrangement. Okay, in such a way that you're going to have a more generalized form. Okay, you see here is this is Sc, this is R. Okay, so if possible that you actually can try to times the above with Sc. Okay, here you times by Sc, below you times by Sc as well. Then what you will have, you have 1 here, then you have Src plus 1. Okay, so this is your Hs. And then if you want to get the magnitude, okay, if you want to get the magnitude is always positive, right? Okay, so if you see all this one is in Hs. Okay, then you can change it to like this j omega, because this is actually when the steady state, when this is 0, it is equal to j omega. So now if you want to see the magnitude, so the magnitude is 1 square, then you have the j omega, right? J omega, S is equal to j omega. J is equals to what? J is equals to this one, right? Then you have omega RC square. Okay. You know the phase, okay, is HUB over C, right? As we learned before. Okay. So now we have a negative there. Okay. Now we have a negative tangent, negative 1. Okay. This is your B and over your A. So you have omega R C. Okay. Okay, you see this is magnitude, right? So it is always positive. Okay, it's always positive. And when actually you have this, this is your way to find your angle, which is the negative inverse tangent. Okay, B over A. Okay. And next, sorry, I don't feel really well. So if anything that I miss explain, please let me know. Okay, because I'm not really feel really well. Okay. Next, given the transfer function of a network, given that S 10 to the power of 4, S square plus 2000 S plus 5 times 10 to the power of 6. Evaluate the transfer function H omega equals to 1000 radian per second and omega equals to 3000 radian per second. So you have 1000 radian per second and omega equal to 3000 radian per second. Okay. You need to evaluate here. Okay. So 8 omega equals 1000. Okay, you just plug in because you know that actually S is equal to J omega, right? So J omega 1000 to the power of, is there any power? No power because this one is S to the power of 1. So that's why we only have J 1000. And this one we have power, which is power of 2. So we have to put J omega power 2. Okay, power to the power of 2 or square. And then we have J 1000 here and accordingly. And then you can see here, this one is J 2000 to the power of 6 and this one is 5 times 10 to the power of 6, which is this part, minus 10 to the power of 6. Okay. Here, where the minus come from? The minus come from the imaginary numbers, okay? Which is this, just now. Which is j equals to negative, square root of 1 of negative 1. Then if you have j to the power of 2, you're going to have negative 1, okay? So that's why you have negative here, okay? Which comes from here, okay? And then you do the simplification, you obtain j10 plus 4j2, okay? And then you can see you can introduce what is equals to j. Remember Euler's formula? Do you remember Euler's formula that we learned before? Remember Euler's formula? Okay, I won't try to write this completely. You try this yourself, okay? What is Euler formula relating to sin and relating to cos? Okay, this one is not complete, huh? But how in such a way that we manipulate this term in order that we're going to have j can be replaced with ej term. Okay, here where our j is actually replaced by ej 90 degree. Okay, which part of here that have j? Is it here or is it here? Okay, you can refer to appendix, or if you want to see whether you remember or not, you can actually able to answer it right away. Then you substitute this j with your exponent equivalent, which is here. And then here, 20 is actually you obtain from 4 square plus 2 square equals to 20. Okay. And then what is this? Okay. So you can see how you actually obtain these things. Okay. 26.6 angle. This one is almost similar to this one. Okay. In order to have j, you need to represent it with ej 90 degree. But how about this if you want to make a simplification? Okay. Try using Euler's, try at your own home how you actually obtain this. And then 10 divide by 20, you get 2.24. Okay. And this one, because it is like index, so it is 90. It's 90 minus 26, so that's why you have 63.4 degree. Okay, same goes for omega equals to 3000. Okay, the number just changed, but it's still the same operations. Okay, you can try this at home. Now example 3, find the frequency response of the system shown below at frequency omega 1. Okay, sorry, this one should be in the, please correct your own slide. Okay, all of this is actually subscript. Omega 1 1000 pi, omega 2 3000 pi, omega 3 3000 pi, omega 4 7000 pi. You can see here, okay, I would like to point out because it is often than not, often that it is make a mistake in the x-axis. Here mentioned that omega 1 equals to 1000 pi. So means that omega 1 is equals to 1000 pi. If it's mentioned omega 1 equals to 1000, means 2 pi f is equals to 1000. So it is not the same. Okay. For example, this is totally not the same. Omega here is 1000 pi, and then here is omega equals to 1000. They are not the same, but that's why I would like to point out, because students always make mistake here. Okay, sometimes they put pi, sometimes they don't have the value of pi. It depends on the question. So let's say for this one, for this condition, it is 2 pi f. So what is your frequency actually? Your frequency is actually 1000 over 2 pi, which is what? Which is 500 over pi. Okay, so how about this one? This one is 1000 equals to 2 pi f equals, f is actually equals to 1000 sorry, here is 2 pi, 1000 pi, so pi, so you cancel out, so you have 500. Okay, so how about this one? You have f equals to 1000 over 2 pi, so it is 500 over pi. Okay, if you notice, f1 and f2, they are not the same. So make sure you really take note on this when you answering question. Okay, make sure you don't make mistake here. Whether it's omega or it's f, and whether it is pi or is it without pi or something else different from, depends on the question. You guys need to see it properly. Okay. Now, find the frequency response of the system shown below at frequency given here for frequency. Given the value of R is 200 pi ohm. Okay, remember there is a pi here. And given the inductance, which is 0.1 Henry. So V2 is actually the voltage measured across the resistance. Okay, the solution. So by voltage divider first, okay, to find the frequency response of the system for each frequency, we need to evaluate the transfer function. So you see V2 over V1. So this is R is actually coming from the voltage drop measured at across V2, and this one is actually the total voltage. Okay, you know that this one is IR and this one is also IR because they are series, so their current is the same. So we can omit the current factor, so only leave the resistor, just like in the previous examples. Okay, example number 1. Okay, so and then you substitute at steady state. You have actually your S. Okay, at steady state, S is actually equals to j omega. So that's why you have j omega here. And then you need to simplify the function so that it have more generalized form with one here and one here. So if this that you have here is actually j omega L, okay, and this is R. So actually in order to have generalized form where you have one here, so R divided by R and R divided by R here. So you will have 1 over 1 plus j omega L over R. Okay. So which is shown here. The algebraic expression for the transfer function may be simplified in form by dividing WP Okay, we can call it a corner frequency, or we can call it a critical frequency. Okay, they have two names at least. So this one is subscript as well. Okay, the algebraic expression for the transfer function may be simplified informed by defining the omega p equals to R of L. Okay, R of L means R numerator, L denominator equals to 1000 pi. Okay, omega p is sometimes referred as corner frequency. We can also refer it as a critical frequency. Then you have Hj equals to tangent, negative inverse tangent, omega over omega p. Okay, you defined it. Omega p equals to RL equals to 2000 pi. So if you move to here, okay, the equation, omega R over L is 200 pi divided by L. Okay, R over L. So this one is 0.1. So that's why you have 2000 over L. Okay. And that's why you have 2000 pi. Okay, that's why you have 2000 pi because 200 pi divided by 0.1. You should have 2000. 2000 pi. So at omega 1, okay, this is the angle. Okay, you can have, this is the formula. Okay, negative inverse tangent omega over omega p, which is R over L just now, and then over 1 plus omega p squared. Okay, make sure you make the generalized form here first. Okay, you need to make sure that you achieve to this generalized form first. Okay, and then hj omega magnitude, with the magnitude, there is a bit error here. This one should be, there is another close bracket here, and then angle. Okay, and then you have your angle for that. Okay, at omega 1, omega 2, omega 3, omega 4, if it's given that omega 1 is equals to 1000 pi, if you see from the previous example, previous information, omega 1 is 1000 pi. So you put here 1000 pi, negative tangent, 0, negative inverse tangent. Ini kelas saya padahal. Sorry for the disruption. Zero. So you have this one is omega. So you replace this with 1000 pi. So 1000 pi divided by 2000 pi. This why you have 0.5 here. Okay. And then 1 plus okay, 0.5. And then here is actually 1 plus omega here. You replace with 1000 over 2000 pi. Okay. And then because it is to the power of 2, so that's why 1000 pi divided by 2000 pi, you actually have half, right? 1 over 2. So 1 over 2, 1 over 2, you have 0.5, 0.5, and then you square it, you're going to have 0.25. So that's why you have 0.25 here. Okay, and then this is half is actually coming from the square root. Okay, so you have 0.89 phasor negative 26.6. Okay, this is the angle. Okay, so you can see so the angle is actually negative. If you put your inverse tangent, plug in your calculator, inverse tangent 0.5. Okay, then you put the negative at the front, you have 26.57. So the magnitude is coming from the below. Okay, so the same go for the other parameters. Okay, the other parameters. I mean, for the other omega. Frequency response describe the output amplitude. Okay, frequency response describe the output amplitude, and the amplitude. Okay, here. Okay, I make the red first so that it's more clear. Okay, frequency response describe the output amplitude and the output phase of the network. Okay, generally it is in the form of a filter function. Usually we are interested in plotting both, okay, both the magnitude and the angle of the transfer function versus the angular frequency. This one is usual, okay, but this one is for the you know for the filter function. But we have been familiarized, right? Our x-axis is at the time domain or omega domain, okay. But nothing changed so much. We still this one our magnitude and angle over the x-axis here, which is the angular frequency. So output amplitude is actually you see here output amplitude is h j omega times input amplitude, which is gain. So I'm not sure if I can. Okay, I can. So you have this h j omega. Okay, now you want to know the gain. You want to know the gain of your you can call it as gain. Okay, so you have this is output over your input. Okay, so if you want to know the gain, you can see here this is your output. Okay, you want to rearrange output over your input. Okay, so this is the gain. Okay, the gain. So this is output amplitude, this is input amplitude. Then you have a output phase, which is input phase plus phase. Okay, output phase plus equals to input phase plus uh, the phase. Okay, the phase of your trans your frequency response, which is your transfer function. This one. Okay, the phase of your h. Okay, so it is in plus form. So you need to see this properly. Okay, this one is multiply, and this one is plus. Okay, so this is your gain, and this is your phase. Okay, to obtain the output phase. So frequency response plot. Okay, a semi-log scale. Okay, you will see this graph. I'm not sure whether you've seen it before. Graph semi-log. Okay, how is it look like? Okay, later on I will show. It's used to plot frequency response because range of frequency may span several order of magnitude. Hence, log scale can be helped to compress data. For example, if you have one data which is which is for example 50 in value, then the next data is actually 500 or 5,000. So you cannot, in normal graph, you cannot plot this effectively because the range between one data to the another data is very wide. Okay, and sometimes it can be very narrow. Okay, but this one is normally is for several orders of magnitude, where it's actually a lot. The data 1 to data 2 is very wide of a range. Okay, for example, if you want to put into the graph, it's quite impossible to put in the normal graph data 1 50 and data 2 5,000. It's not possible. However, in Semilog, we can do that because we have we have this characteristic in Semilog scale graph, which enable us to plot the data which have variation where the one data to another data is different in the order of magnitude. For example, multiple of 10, multiple of hundreds. Okay. Decimal scale leads to computational simplicity. The gain Hj omega, which is the magnitude here, okay, is usually expressed in decibel scale and defined as, if you see, Hj omega in dB scale is actually 20 log 10 Hj omega. This one is linear scale. For example, if you have a transfer function of Hj omega of 0.5, so 20 log 20 20 log 0.5, so you will have negative 6.02. So I think this one you sorry. So this one is I think this one you know, right? This one is best. Okay. Okay. Sorry for the error. A Bode plot is used to simplify. So the name here is already shown here. Okay. A Bode plot is used to simplify the frequency response plot, since it is tedious to plot the transfer function for the whole span of frequency range. Okay, this is what we call as a Bode plot on semi-log scale graph. Okay. Two plots. Okay. Now we go to the introduction of Bode plots. So in Bode plots, we have two plots, which is both actually have logarithm. Okay, logarithm mean you're going to use log. Okay, 20 log. Both have logarithm 20 log of frequency on x-axis. In y-axis, magnitude of transfer function. Okay, so the word here magnitude in decibel, so 20 log. And then another y-axis, you can have phase angle, which is theta omega in degree. So you have two plots, which is one magnitude versus the omega, and then you have phase angle versus omega. Okay, can be used to interpret how the input affects the output in both magnitudes and phase over frequency. Okay, interpret how the input affects, because you know, right, it's actually a relation between input and outputs. Okay, which is your H. Okay, so this Bode plot can be used to interpret how the input affect the output. Okay, at both term, which is your magnitude and your phase over variation of omega. So first step in actually drawing these Bode diagram lines, okay, first you need to determine the transfer function of the system. HS, this is your output and this one is your input. You do need to determine the transfer function first. For example, in here, you have Ks in bracket S plus Z1 over S plus P1, S plus P2. And then we need to rewrite. Okay, we need to rewrite so that we have the standard form. Okay, we have the standard form. Standard form in such a way that this one is actually need to be 1 plus S over Z, or 1 plus S over Z1. And here is 1 plus S over P1, and also here. Okay, if you see the initial here, we have actually like this. However, this one need to be turned to 1, this one need to be turned to 1. So that's why S divide by Z1, and then Z1 divided by Z1. Same goes to here, S over P1. And then where does it go? When you actually divide this by Z1, and this y1 you have it here. Okay, this why you have it here. So now you have kz1 and you have p1, p2. Okay, this is the you accumulate here the form. So this is your s, and this is your numerator and denominator need to be rewrite so that you have the standard form, which is 1 plus some s over zeros, or 1 plus s over the pole. Okay, replace s with j omega. Now you know that at steady state you have s equals to j, you have s you have s equals to, okay, at steady state this one is 0. Okay, so you have s equals to j omega. So you're going to replace s with j omega. So you put here j omega, j omega, j omega, and j omega. We can rewrite hj omega as, after you've been replacing it, okay, you have here k naught. Okay, this is your k naught. K naught is actually kz1 over p1, p2. Okay, so summarize as k naught. And then omega j. How you get this j? Euler's theorem. Okay, it's actually omega 90 degree. You put in phasor form also, it's actually 90 degree. And then m1 theta 1, m2 theta 2, and m3 theta 3. Okay, so m, this one is actually this one, and this one is actually this one, and this one is actually this one. Okay, so find the magnitude and gain of the transfer function in your dB. So you have 20 log hj omega equals to 20 log. This one is the magnitude in the this is the value in the decibel, the magnitude. So k naught omega m1, omega 2, omega 3. Okay, so the gain in dB is actually 20 log. Okay, 20 log k naught plus 20 log omega plus 20 log m1 minus 20 log m2 minus 20 log m3. This one is actually you learn in your mathematics, whether in secondary or in your mathematics engineering, I'm not sure, but you learn this anyhow. Okay, so this is 20 log of all the log here. If it's multiplied, it will become plus. If it's division, it will be minus. So that's why you have minus here. Okay, so this is the gain of in dB. And then how actually you calculate the phase? Okay, the phase is actually, do you have the angle here plus 90 degree, okay, 90 degree which is coming from here, and then plus theta 1, and then minus with your theta 2 and theta 3. Okay, plot of log magnitude. Each of these individual terms is very easy to show on logarithmic plot. Okay, they call it logarithmic because it's in a log scale. Okay, the entire Bode block magnitude plot is the results of superposition of all the straight line term. Okay, you see here the entire Bode log magnitude plot is the result of superposition, means that you're going to add up the individual straight lines in order to have the accumulative, the total of it, okay, of all the straight line terms, to find the effect of each term and the overall effect. We have to understand the effect of different types of term. So in these equations, sorry, here Okay, you can see you have here, and you have this part, and you have this part. Cannot, the numerator part, and the numerator part. Okay. The first is the constant term, which is your cannot. Okay, and then the next one is post and zero at the origins. If we have this one at the origin, which is j omega, and next we have post and zeros. Okay, post and zeros not all at the origin. This one is post not at the origin, j omega over p1. So this is post 1 plus 1 over j omega over z1. This one is zeros. Both of them are not at the origin. This is the form where they are not on at the origin. This one is when they are at the origin, and then depending if they are on the numerator part, they will be regarded as zeros at the origin, and if they're located at denominator part, they will be called as poles at the origin. Okay, for this case, it's not at the origin. Okay, for the below. So you can see the word here. Okay, the difference. So for the constant term, okay, constant term such as cannot, because it only consists of numbers, constant, contribute to a straight line horizontal lines of magnitude 20 log. Sorry, this one a subscript again. Sorry for the error. Okay, cannot. So because it's just a straight line, so let's say you put cannot, for example, 0.5. So 20 log 0.5, you would have negative 6, which is down below. And let's say you have 20 log 2, you have 6, which is here. So they are just straight line over the entire frequency range. Okay, the entire omega. So if you see here, this is our semi-log scale. You can see it is actually in multiple of 10. Here is 0.1, and then times 10 you have 1, and then 1 times 10 you have 10, and 10 times 10 you have 100, and 1000 100 times 1000 times 10 you will have 1000. So you can see we set a lot of range in order for us to able to plot data which have several orders of magnitude of different. For example, if you have 1.5, for example, if you have 2, you can still plot here, and then suddenly you have graph value of 120, so you still can plot. However, in the noble graph, it is difficult to do so because the scale is constant. Okay, however, in the semi-log scale, it is actually a multiples like this, like multiple of 10. Okay, they are different. Next, zeros at the origins. Okay, a zero at the origin occurs when there is an S or j omega. Okay, you know already S is actually equals to j omega at steady state. Okay, multiplying the numerator, which is on the top part. Okay, each occurrence of this cause a positive slope line passing through omega 1 with a rise of 20 dB per decade. So if you see here, okay, this one, if you have j omega at the top part, which is the numerator part, you will have it as a 0 at the origin. So if you're going to plot it, okay, it is actually passing through 1 with a rise of 20 dB per decade. So here 1, and then here is 10. Okay, then you have here is 20 dB, capital B, because this one is dB, 20 dB. So 10 to 1, actually the difference of 20 dB. So that's why you have with a rise of 20 dB per decade. Okay, because this one is decade different. This one is decade multiple of 10. This one is decade as well, multiple of 10. Same goes for this. Okay, so 20 dB per decade, and you can see the gradient is actually positive. The next is pulse at the origin. Pulse is the origin is that where you have S or J omega at the bottom part here. Okay, so how actually we represent them is actually we have a negative slope still passing through 1. However, we're going to have it gradient as negative, which is drops, which is on this trend. So it's negative 20 dB per decade. So you must make sure that this one and One, for example, dot here and then the dot here, in order for you to make a straight line up to 20 dB and at the x of 0.1, which is decade different. Okay, decade different. So this is the pulse at the origin where you have S or J omega at the denominator part, the bottom part. Now, the next is zeros and pulse, not at the origins. So now we're going to have zeros and pulse, which they are not at the origin, means it is a one plus of something. Okay, indicated by 1 j omega over zi, which is your zeros, and 1 plus j omega pulse. The value of zi and pi in each of these expression is called critical frequency, okay, or corner frequency, okay, or break frequency, okay. Below the critical, you can see there is a lot of name, right? Critical frequency, break frequency, corner frequency, okay. Below the critical frequency, this term do not contribute to the log magnitude of the overall plot. Okay, you see here below the critical frequency, so it must be after it, greater than it. Okay, above the critical frequency, they represent a ramp function of 20 dB per decade. Okay, so you can see, right? If you want to plot, okay, we need to consider the value of the term which is after above the critical frequency, not below. Okay, not below. For example, if this is 10, for example, if this is 10, you need to consider the value of the value above the critical frequency, which is 11 or 100, for example, be above, but not below, for example, 5. Okay, not below. We only consider the value above the critical frequency. Okay, and then we represent as a ramp function of 20 dB per decade. You know how ramp will, right? Ramp is actually just a value like a straight line with a constant gradients. Okay, for example, 20 dB or negative 20 dB per decades. Okay, you can see my movement, right, of the cursor. So 0 give a positive slope, which is 20 dB per decade, and while the pulse will produce a negative slope, negative 20 dB per decade. Okay, so this one will give your positive slope, and this one will give negative slope. So you see here, there is Z1, there is P1, and there is P2. So mean you will have a critical frequency. For this one, we contribute to one critical frequency. This one will contribute to one critical frequency. This one will contribute to one critical frequency. So 3 frequency here. Okay. To complete the log magnitude versus frequency plot of a Bode diagram, we superposition all the lines of different terms on the same plot. Okay. If you notice here, okay, from the example here, this one is a zeros, not at the origin. Okay, and it is zeros because you can see here z, and if it's not given, when it's like this, it's actually 0 because it is the numerator part. So z1, so z1, for example, here is 0.5. Okay, because it is in the middle, and then it is not origin, not at origin, so we only count the value after. For example, here. Okay, so give rise about 20 dB per decade. So this one is zeros, not at origin. Then we have this one, pulse, not at the origin, because because it's pulse and at the numerator part, the slope is actually drop. Drop means in terms of drop, negative 20 dB per decade, which is this. Okay, decibel is actually D capital B. Okay, this one also a typo there. Examples. Okay, sketch the Bode log magnitude diagram for the transfer function given. Are they giving the step to you? Okay. Let me try. I'm dividing screen right now. Okay. Um, so you are given the HS. Okay. Hope you can see the screen. Huh? You given HS, which is 1 over 2s plus 100. Okay. So one of the things that you need to uh, you need to you need to transform first into a generalized form. Okay, the standard form. Okay, so this one should be 1. So how you make this one equals to 1? You need to make this one is actually 100 divided by 100. Am I correct? So but let me like this first. A bit slow, but so that you understand. Okay, then you take out the 100, then you have 1 here, right? And then how about here? This one is 2s. Okay, so 2s over 100. Okay, and then this one need to be like coefficient of 1. Okay, the standard form. So 100 over 1 plus s over 50. Am I correct? So this one is 50. Okay, so you have this is actually 1. I don't have the semi-log, but you can use the semi-log. Okay, so what is your 20 log 1? Okay, for the above term, so you have 10 dB. Sorry, 0 dB, 20 log. Okay, 20 log 1. You have 0 dB here. Okay, and then you have 50 here. Okay, pulse not at the origin. So it should be negatively sloped, right? But at 50. Okay, at 50. So you're going to have a value. Okay, if this is shown by black, okay, okay, and this one is like like shown by black color, not negative. I'm just want to say this is a black color. Okay, and then this one, okay, we only have the value after it. Okay, like what we told just now, we only consider value above the critical frequency. Okay, so you have here, which is your um, 50. Okay, which is your 50, and it's actually because it is post at not at origin, and then it is at the numerator part. So this one is will be negative 20 dB per decade. Decade y is a several order of tens, right? So combine, you have this. Okay, then you have, don't forget about this. Okay, so this is 1 over 100. 1 divided 100 is actually 0.01. And then you take the log scale, which is 20 log 0.01. You have negative 20 dB. You have a straight line here. Where can I put? Okay, negative 20 dB. So this one, all of them will be bring down by negative 20 per dB, by negative 40 dB, because you have this, right? This one is actually contribute 20 log 0.01. Am I correct? Wait, yes, 0.01. So you have negative 40. So all of them bring 2 down because of this guy. So minus. So you have the new the finalized one, which is this. Okay, negative 40 dB. Okay, Okay, so this is it. And then this is the semi-log graph. Okay, you see here in multiple of 10, that's why you decade 10 to the power 0, which is 1. 10 to the power 1 is 1. 10 to the power 2 is 100. 10 to the power 3 is 1000. And this one is 10 to the power 4. Okay, so it's a decade difference, 10 times difference. Okay, the next is find the find the Bode log magnitude plot for the transfer function. So you try this at home. Okay, you try this at home. You plot each individual line first, then you will take the superposition, the effect of all of them. Okay, try this at home. Since you have the answer already. Next, plot of phase angle. To complete the full Bode diagram, we have to plot the phase angle versus input frequency. Just now we have the magnitude. Now we want to have the phase angle as well in order to complete our Bode diagram. Bode plot or Bode diagram is the same. Okay, lines can be drawn for each of the different terms. Then the total effect may be found by superposition, adding all of them. A positive constant k greater than 0 have no effect on phase because there is no phase. However, if we have a negative constant k less than 0, this will be creating a phase shift of plus minus of 180 degree. Sorry, there is seems okay. Sorry for the typos everywhere. Okay, so theta omega is equals to angles of k naught. Okay, if it's negative, we will have phase shift. However, if you have positive constant, no effect on phase. 90 degree plus theta 1 minus theta 2, theta 3. So this one is coming from zeros at the origin, right? This one coming from zeros not at the origin. This one coming from poles not at the origin. And this one coming from the another poles at the origin, should you have another one. Remember, real versus imaginary plot, a negative real imaginary number is at positive or minus 180 relative to the origin. Okay, a negative real numbers, okay, is actually 180 degree relative to the origin. Effect of zeros at the origin on phase. Zeros at the origin, j omega, cause a constant 90 degree shift for each zero. Okay, like I told just now, this one is coming from zeros at the origin. Okay, so here is the plot angle transfer function, angle of the transfer function TF, and then over the omega, which is plus 90 degree if you have zeros at the origin. Next is poles at the origin. If it's pole at the origin, it is converse, which is negative 90 degree. But however, it's the same as zeros at the origin, which is a straight line passing through the entire frequency range. And then if you have effects of zeros not at the origin on the phase, okay, zeros not at the origin, 1 plus j omega zi have no phase shift for frequency much lower than zi. Okay, just like in the magnitude, right? We only consider value above that. Okay, above that. So we don't consider before. Okay, and then a positive phase shift at zi. So you can see, and then later on I will go to it. A 90 degree shift for frequency much higher than zi. So to draw the line for this type of term, the transmission from 0 degree, sorry, a lot of typos here and there. This one is all the degree. Okay, I hope I don't miss anything. But if I miss anything, you know, right? It's actually a decrease symbol. To draw the line for this type of term, the transition from uh, 0 to 90 is drawn over 2 decades. Okay, because 90 degree, right? If this is 45 shift at Zi, and then 90 degrees is like doubles. So they need to pass through 2 decades. Okay, starting at 0.1 Z1, ending at 10 Z1. So if you see here, sorry. So if you see here, ZY, okay, ZI passing through here, okay, this one is actually at 45 degree, okay, the angle 45 degree, straight line. And then the next one after 1 decade is 90 degrees. But the difference of this range is actually 2 decades. Okay, 2 decades mean 2 times 10, 20, 20 times different. 1 decade, 1 decade, 10 times, 10 times. Okay, so 0.1, and then going up because it says zeros no origin, going up 45 passing through at Z1, and then another one to 90 degree. So this one is transition from 0 to 90 degrees. Okay, this is your Zi. Okay, so you can see the word here, right? Much lower, much higher. Okay, effects of pulse. Now pulse not at the origin, this means that this pulse at the numerator parts. So you're going to have a negative, you're going to have a different kind of curve, even for a different kind of plot, even for the phase. Okay, pulse not at the origin have a no phase shift for frequency much lower than pi. This is pole, okay, and then a negative 45 degree, you can see it is negative. Sorry, there is a typo again because I'm transferring my slide actually to new slide, and I'm doing some, when you transferring, it's not really properly transfer. Okay, where else I make it wrong before I look at this one? I mean, typos are everywhere. But hopefully, if you see that something that I miss, um, it's not intended, and hopefully you understand what is it. Or if you're confused, you just let me know. Okay. So for post, not the origins, if we want to see on the face, okay. So negative 45 shift at pi, okay, and then a negative 90-degree shift for frequency much higher than your pi. So here, okay, to draw the line for this type of term, the transition from 0 to negative 90 degree is drawn again over 2 decades, however, in different trend like this, which is the negative angles, okay? 0, negative 45, and negative 90 degrees, okay? You can see here is negative 45 shift at your pi, okay, which is here. Example 3, for the transfer function given, sketch the Bode diagram which shows how the phase system is affected by changing the input frequency. For the transfer function given, sketch the Bode diagram which shows how the phase system is affected by changing the input frequency. Oh, okay. You can try this at home. Okay, first you need to factorize, right? This one, because you have s squared now, 505 to 2500. So you make this factorization where you have s plus something plus x. You know factorization, right? Because this is quadratic form. Okay, and then okay, maybe maybe I show some I mean, I try to give some idea, okay, and you guys can try at home, okay. Let me draw first here. So hs equals to 5 times 10 to the power 4 s s squared plus 5. I try to jot down at the touch screen, which is at the other screen. That's why you guys cannot see it. Okay, so here you can see you make the factorization first. Okay, so you have this s plus 5, s plus 500. So what after that you should do? Okay, I give another hint. You try at home. Okay. Okay, so I just give some hint. You try at home. Okay, so s over 5 plus 1, s over 500 plus 1. So and then x is what? X is what? And then y is what? Okay, try to make, you see this one, I'm trying to convert to the standard form. Okay, try this at home, and it's given here. Okay, so with that I finished the lecture chapter 5 part 1. Okay, see you in the next class or tutorial. Thank you very much for listening.